Have you ever stopped to think about how we actually talk to computers? I mean, we don't sit there punching in ones and zeros anymore, right? We use commands that look almost like plain English. Well, today, we're going to dive into that incredible story, the ascent of code. And really, it all boils down to this one simple question. Deep down, at their core, computers are just a bunch of switches. They only get on or off. That's your ones and zeros. So why on earth don't we just talk to them like that? What's the point of all these fancy programming languages? And the answer is, well, it's pretty wild when you think about it. We didn't get better at speaking their language. Instead, over decades, we taught them how to understand ours. This whole story is about climbing a ladder, getting farther and farther away from the raw machine and closer to how we actually think. Okay, so let's start at the very bottom of that ladder. We're talking ground zero, the language of the machines themselves. This is the native tongue of the computer's processor, and it is nothing but a raw, non-stop stream of ones and zeros. I mean, everything. Adding two numbers, changing a color on your screen, it's all just a very specific sequence of binary. And boom, right here you can see the very first giant leap forward. Look at that. On the left, that's machine code. Total gibberish to you and me, right? But on the right, just three simple letters. ADD. That's assembly language. This was, and I'm not exaggerating, a complete game changer. So that first step up the ladder, that brings us to what we call second-generation languages, or 2GLs for short. And the big player here was assembly. The whole idea was brilliantly simple. Let's replace those impossible-to-remember strings of ones and zeros with something, well, something a human can actually remember. And these handy little memory aids have a name, mnemonics. A mnemonic is just a short, catchy word that stands in for a bunch of complex machine code. So instead of typing out a long binary sequence for add, you just type ADD. For subtract, you type SUB. See? It's a super clever trick to make programming way less of a headache. Okay, wait a second. This probably has you thinking, if the computer still only understands ones and zeros, how on earth does it know what add means? We're not speaking its language anymore, so what's the magic trick here? The magic trick is another piece of software, a special translator program called an assembler. Think of it like a bridge. You, the human, write your code, the source program, using those easy mnemonics. The assembler then takes that, translates it all back into the ones and zeros, and spits out an object program that the computer can finally understand. Pretty neat, right? Here's a good way to think about it. Talking in machine language is like trying to communicate by just clicking a pen. It's possible, but awful. Assembly language is like using short, agreed-upon code words, like Roger or copy that on a walkie-talkie. It's way better, for sure, but you're not exactly having a deep conversation yet. But, and this was a huge but, there was a massive catch. Assembly language was handcuffed to the specific computer hardware it was written for. So a program you wrote for one computer was totally useless on a different one. Imagine rewriting all your software from scratch every single time a new processor came out. It was a total nightmare and a major roadblock. So this huge problem, this need for programs to work anywhere and be easier to write, is what sparked the next great leap. Welcome to the third generation of programming languages. You can think of this as the English revolution in coding. And this is where things start to look a lot more like the programming we know today. The goal was crystal clear. Assembly was still just too hard, too slow, and way too easy to mess up. What we needed were languages that you could learn easily, write code in quickly, and, crucially, that other people could actually read and understand without pulling their hair out. And this revolution? It gave us the absolute titans of the programming world, the languages that literally built our modern digital lives. I'm talking about names you've definitely heard of: Python, C++, Java, C#. These are all third-generation languages, also known as high-level languages. And just look at this. This right here is a complete working program in Python. All it does is print "Hello World" on the screen. That's it. It's simple, it's readable, it's almost plain English. Can you believe how far we've come from that mess of ones and zeros we saw at the beginning? And here's a little fun fact for you. One of the very first pioneers of this 3GL wave was a language called Fortran. The name is short for Formula Translation, which tells you exactly what it was for. It was built to help scientists and engineers crunch some seriously complex numbers. Okay, so let's go back to our analogy. If the second generation was like using walkie-talkie codes, the third generation is like speaking in full, proper sentences. We're using familiar words, we're using logic that makes sense to us, and we have a new, much smarter translator, called a compiler or an interpreter, that does all the hard work of turning it back into machine code for us. But, of course, the story doesn't end there. We kept climbing. The next step up the ladder takes us to the fourth generation. And this is where the whole philosophy of programming kind of flipped on its head. The focus was no longer on the how, it was all about the what. And that right there is the absolute core of a 4GL. You stop telling the computer how to do every little thing. Instead, you just tell it what you want. You declare the end result you're after. And these languages are insanely powerful, especially when you're dealing with massive amounts of data in a database. Just look at this example from SQL, a classic 4GL. It reads just like a sentence, doesn't it? It's basically saying, "Hey computer, show me the names and join dates for everyone in the sales department." You're not telling it how to search the files or how to sort the data. You just state your goal and the computer does all the heavy lifting.
I love this analogy. Using a 4GL is like going to a chef and just saying, "I'd like a cheese sandwich, please." You don't give them a recipe, you don't tell them to get the bread, find the cheese, turn on the grill. No. You just state what you want and you trust the expert, the chef, or in our case, the computer, to handle all the steps to get you there.
All right, let's zoom out for a second and look at the big picture here. This whole journey, this whole story, has been about climbing up that ladder. With every step, we've moved farther and further away from the nitty-gritty, complex language of the machine and gotten closer and closer to the way we think and speak. This table really lays it all out perfectly. We started with 2GL. Hard to use, looked like weird codes. Then we climbed to 3GL, way friendlier, looked kinda like English. And now we're at 4GL, which is super intuitive and feels like you're just asking for what you want. Each single step made programming easier, more powerful, and available to way more people. And that's the core of it, isn't it? The entire history of code is about one thing: shifting the burden. We started out by forcing humans to twist their brains to think like a machine. And now we've successfully taught the machine to understand us. It's a total reversal. So that leaves us with a really fascinating question, right? We've gone from raw binary all the way to nearly plain English. So what's the next leap? What's the next rung on the ladder? Are we heading for a fifth generation where you just talk to the computer about your idea and it writes the code for you? Or maybe a language where you don't even have to type at all? One thing's for sure, the ascent of code is definitely not over.